Hi everyone. So this video here should be watched after you finish watching all the videos in Chapter 1. And briefly, it's a quick demonstration of a lot of the fundamental algorithms that you've seen in Chapter 1. The first one that I'd like to demonstrate is algorithm 1.1, which is how to draw samples from an exponential distribution. Now, we've already seen in the previous computational video that Python already has a function that you can call to draw samples from an exponential. But either way, here we're going to do it in sort of the, we're going to code that function up in some sense following the tools that we have learned in Chapter 1 in order to just simply show that it works. And that's going to become very useful in case you start using a language, or even Python, you start drawing distributions from or drawing random variables from a distribution for which there doesn't exist a previous function. So let's go through the packages that we'll need: numerical Python, the math package, and the plotting package. I'm going to want to generate 10,000 samples. Here I'm going to set my counter to 0. So as I start iterating through my algorithm 1.1, and finally I have to specify a parameter for that exponential distribution. Remember, the exponential distribution only has a single parameter, and here we've called it a rate. Previously we called it a scale. I've explained why it can take on the two different names. Typically in mathematics literature it's called a scale. In the physics or chemistry or natural science literature, normally that scale takes on a meaning of rate, so we call it a rate. So if we remember from Chapter 1, we have to compute an inverse CDF. So now I'm going to define an inverse CDF function, and my inverse CDF is going to take on two separate values, or two separate arguments, I should say. The first is the scale that I plug in, and the second one is the uniform random number that I generate. Finally, I'm going to generate an array of 0, so I'm going to pre-allocate, I should say, memory with an array of zeros of size equivalent to the argument that I use here, numerical samples. And here's the single loop that I need to use in drawing samples from a continuous distribution, assuming I can compute an inverse CDF. So I'll start off with the counter, which I've initialized, if you remember, at 0. And provided that counter is less than the number of samples, so that sort of sets a condition at which to end the while loop, then I generate one uniform random sample between 0 and 1. If I haven't specified that additional comma 1 that implies that I want to generate a single number, then I plug in that random sample into my inverse CDF function. And remember, as the argument for the scale, I'm using the numerical value for the rate, which I had specified as 3. And then I iterate my counter by 1. So if I notice, what I'm doing here is that I'm populating the pre-allocated vector, exponential samples counter, which had been pre-assigned to a bunch of zeros, to realizations of the exponential distribution. Great. So now I have an array with 10,000 draws from an exponential distribution. Depends what I want to do with this. Maybe I want to use those samples to compute a mean. Maybe I want to compute their variance. There's all kinds of things I can do with those samples. Another thing that I can do is also plot them or histogram them. So I'm going to histogram them in exactly the same way that I had earlier by first generating first specifying what I want to plot, the number of bins, the shade, the color of the bins, the edge colors, and then I can specify X labels, Y labels, and title, and finally show the plot that I have here. So this was, I see, it says here plot for 1,000 samples. Well, in reality, this should be 10,000 samples if I specified this to be 10,000. So let's go ahead and run it again, and we should obtain a histogram which is just as smooth. And it's complete. So we notice here that the code, in other words, algorithm 1.1, generated samples which look very much like they're drawn from an exponential distribution. In fact, we notice, again, that to save time, we didn't need to go through this algorithm 1.1 for this particular simple example. We could very well have used a built-in function in Python. But again, in case we need to sample from distributions for which we don't have pre-built functions, and it's useful to know how to draw samples from a distribution in general. So here's a different example. This is algorithm 1.2 for drawing samples from discrete random variables. Now, if you remember, this code is going to require two loops, or two nested loops. So just to sort of wrap our head around it before we start explaining the code, if we go back to algorithm 1.2, we notice that we have an outer loop, basically telling us how many samples we want to draw from our discrete distribution, in this particular case, the categorical distribution. And then we also have an inner loop where we have to compare the uniform random number to the probabilities of the individual categories, or the probabilities of the individual events. Right? So we notice here outer loop, inner loop, just like we would have explained in chapter 1. So let's go ahead and explain how this code works. We have to first import our package to get sort of our numerical Python to get the desired functionality as I specified here. We specify how many samples we want to generate, which is 1,000, and we set our initial counter to 0. Well, if it's going to be a three-dimensional categorical distribution, then I'm going to specify first the three probabilities of the individual categories or events. So the first event will have probability 0.2, the second will have probability 0.3, and the third will have probability 0.5. And we notice immediately that if only three events are possible, then the sum of their probabilities must be equal to 1. And so here we have 0.5 plus 0.3 plus 0.2, which is equal to 1, as expected. I'm going to pre-allocate memory again with another vector, an array, that I'm going to call frequencies. And that's going to have entries, all zeros, 0, 0, 0. My frequencies is the one that I'm going to be populating as I run my algorithm 1.2. In other words, when I draw an event that belongs to category 1, then this element of the frequency, the first 0, is going to become a 1. If I draw an element from the second category, it's the 0 that's going to become a 1, and so forth. So here we are, the while loop. So while the counter is less than the number of numerical samples, that's specifying basically run this while loop for however many numerical samples I have. Initially set the category equal to 0. Then finally start a cumulative sum of elements. So we start by saying that the probabilities are equal to, the probability is equal to 0. Remember, we're going to be constructing a CDF for my discrete distribution, and draw a single uniform random sample from 0 to 1. Finally here, initially, if my random sample is greater than my cumulative sum of elements, then update my category to the next category, and update the cumulative sum of elements by adding the probability of the next category. So this is how I compute my CDF, or this line here is how I compute my CDF for the discrete distribution. Finally, once this loop is done, this while loop is done, then increment the frequencies for that particular category that you've selected by 1. And then for the outer loop, update the counter by 1, and then keep iterating. So it's a little bit more complicated than the random sampling of the uniform, or I should say of continuous random variables, remember, because we have this sort of internal structure here. We can't calculate or pre-calculate sort of an analytical, or I should say here we're calculating the sum of the probabilities for each event as we go. Finally, what do we do with the frequencies we have? Well, I'm going to do something. I'll take the sum of those frequencies. So suppose that I've seen event 1 500 times, event 2 500 times, and event 3 501 times. Then the sum will be 1501. And then I'm going to take the individual elements of those frequencies and divide them by the sum. So my normalized frequencies should look a lot like these starting probabilities. That, in some sense, is going to be my test. In technical language, my unit test. Are the normalized frequencies that I'm drawing converging to my probabilities in the limit of a large number of samples? And finally, here what I'm going to do is I'm going to plot or print the normalized frequencies. Then here's kind of my unit test, if we want to call it that. I take the difference between the probabilities and the frequencies. Now remember, in order for me to take the difference between the two, or I should say, in order for the difference between the probabilities and the frequencies to be meaningful, I have to remember to normalize these frequencies. In other words, to divide the frequencies by the sum of the frequencies. Then they become probabilities, or probability-like, and then I can take the difference between the two and verify that the difference is indeed very small. And in fact, if we go back to what my probabilities were to start off with, it was 0.2, 0.3, 0.5. What do we get here? Well, by the time we have, and I should go back, this was 1,000 samples, we have 0.206, 0.304, and 0.49 for the normalized frequencies. So pretty close to what my starting probabilities were. And if I take the difference, then I notice that the difference is indeed quite small as compared to sort of the bare probabilities themselves. So this example here, again, is algorithm 1.2. Now for the next example. This one here is ancestral sampling that we've discussed briefly in class, or in the context of Chapter 1. It's an interesting example because, in this particular case, this would be a case where you have a two-dimensional distribution and you can construct the marginal, and let's say two-dimensional distribution, P of R1, R2. So you assume that you can construct the marginal, P of R1, and then you assume that you can then construct the conditional as a result, P of R2 conditioned on R1. So for this particular case, I've chosen the example of the two-dimensional Gaussian. Now, some people may know that there are different ways, in fact a more direct way, of sampling a two-dimensional Gaussian which does not involve ancestral sampling. So again, this is one of those cases where I don't want to introduce distributions that are too complicated at the beginning. So I'm going to demonstrate ancestral sampling on a simple distribution. In this particular case, this will be the example, as I've mentioned, of the two-dimensional Gaussian. So the two-dimensional Gaussian has a mean array, the array sort of the x and the y value, let's say, for the means, which I'm setting equal to 0 and 0. In other words, it's centered at the origin. And there's a covariance matrix, and that covariance matrix I specified here is 1, -0.8, -0.8, and 1. If the off-diagonals had been 0, then in some sense, this example of ancestral sampling would be very trivial because it would imply that x1, or my r1 and r2, my two random variables, are decorrelated and I can sample them independently. So in some sense, what makes this example a little bit interesting is the fact that I have off-diagonal elements in my covariance matrix. I should say that I can't specify covariance matrix any way I like. Just like I have to make sure that the variance in a Gaussian is positive, there are also restrictions on a covariance matrix, which we'll discuss in more detail later on. But either way, for now I've specified something which is a little bit non-trivial, so the two variables are correlated by virtue of the off-diagonal elements in the covariance matrix. So here, there's a little bit of math, and it's worth explaining what it is we've done to justify the equations we've written down. Remember that when we do ancestral sampling, we first have to sample from R1, and then we have to sample on R2 conditioned on realizations of R1. So you can assume that I've taken my Gaussian with this mean and this variance, covariance that I have specified here, and I've marginalized out R2. Then this gives me a mean for the marginal distribution of R1 and a covariance, or a standard deviation basically, for the for the distribution in R1. Now, I also need the distribution of R2 conditioned on R1. That requires me to start off with a joint distribution, just like we discussed in class in chapter 1, R1 comma R2 divided by the marginal of R1. So assume that I've done that math, and what we find is that the mean of R2 given R1, where that conditional is also a Gaussian, if we do the math, and we find that the mean takes the following form, and the variance takes the following form. So what I've done in the step here that I skipped previously is simply to draw samples of R1, and in this particular case to draw 1,000 samples from R1. It's going to be a Gaussian with the following mean and the following variance. Now, again, the variance and the mean for the conditional distribution are a bit more complicated, and they're given by these expressions here. But given that I have these, I can now draw samples for R2 conditioned on R1 by using the following expression, by using the appropriate mean and the appropriate variance. Finally, I can generate an array, or a two-dimensional array, of R1 samples and R2 samples, and I can plot them. So remember now I'm drawing samples from a two-dimensional distribution. So I've drawn samples from R1, and I've drawn samples from R2 conditioned on R1. And now I have a choice as to what to do, and what I'm going to do is to literally plot the individual data points that I draw. And this is the distribution that I draw. Notice how it's slanted. And it's slanted because the variables R1 and R2 in this particular case are correlated. Again, if I had chosen diagonal covariance matrix, let's replace this 0.8 by just 0 and rerun this, I will notice now that my samples drawn from my two-dimensional Gaussian are actually roughly symmetric around the origin. Any asymmetry is because of finite data effects. And if I had sort of positive off diagonals, then I will notice that the slant of the Gaussian goes the other way. All right, so now the variables are correlated, and my two-dimensional draws from my Gaussian are slanted in sort of this positive direction. So this is an example of ancestral sampling with Gaussians, two-dimensional Gaussian. Let's move to what I believe is the last example, and let's check, yep, in chapter 1. And this particular case here is a demonstration of likelihoods. So what am I doing? First things first, I'm going to import my numerical Python and my plotting function, or my plotting library, I should say. And what I want to do in this example is redo example 1.16 in chapter 1 that had to do with sort of looking at likelihoods as a function of a particular number of coin tosses for Bernoulli draws. So I'm going to assume that 0.3 is the probability of heads. I don't need to specify the probability of tails because I know that that's going to be 0.7. I assume that the number of tosses, I've specified a number of samples in a way, at 1,000. And finally, I generate a number of Bernoulli, either heads or tails, random samples here. And in fact, I'm going to generate 1,000 of them with probability 1 minus p for tails and p for heads. Now, the number of heads I know is going to be equal to the sum of samples, because the idea here is that if I select heads, then the sample value for that outcome is 1, and if I select tails, then it returns as 0. So the number of heads is equal to the sum of the samples, because the zeros, the tails, don't add into the sum. And finally, the number of tails is simply the total number of tosses minus the number of heads, which sort of makes sense. Okay. Next thing I can do is I can do one of two things. I can either sort of define a log likelihood, or I can define a likelihood. I can do both. I don't need both, but I can plot one or I can plot the other. Now, in general, we've discussed sort of in chapter 1 a little bit that we may have to work with log likelihoods very often, and in part that's because likelihoods can become extremely small numbers and cause numerical underflow. So generally speaking, oftentimes we work with log likelihoods and not likelihoods themselves. But either way, here we've done both, and we've defined sort of the likelihood for those Bernoulli draws. Those are given in the textbook itself. So these expressions are derived and given in the textbook. Finally, what we're going to do is, essentially plot the likelihoods as a function of x values here. So the x values are going to be between 0 and 1, and I'm going to choose to sort of increment them by 100. And if I were to plot or interpolate what the likelihood looks like, it looks pretty sharp, centered at 0.3. In some sense, exactly what we would expect. As a dotted line here, I've added the ground truth. It's always helpful when I test methods or I develop methods to sort of generate synthetic data and make sure, for example, that eventually my calculation coincides with the ground truth. Now, I knew here that the probability of heads was 0.3. So my ground truth I put as a dotted line here at 0.3. What I see here is a distribution which is pretty closely centered likelihood whose maximum is pretty close to 0.3. Now, if I were to reduce the number of samples, let's make the number of samples 100. At this point, we won't have as many tosses, and I would imagine that the mean may move away from the ground truth, or may deviate, or is more likely to deviate from the ground truth. So let's go ahead and rerun this. And what we see here is a small deviation. We also notice that the likelihood is a lot broader, in fact, because we're not as sharply committed to sort of the answer of 0.3. Let's go ahead and reduce this even more to 10. And at this point, we notice immediately the likelihood is a lot broader, and there's quite a bit of a deviation from the ground truth. I can rerun this a second time, and there's going to be a different, in this case, the second time agreed better. Third time, it's slightly biased to the left, as opposed to being biased to the right, just because the number of samples are very small. So let's go ahead and increase this back to 1,000, and show that, again, our likelihood is very sharp, and, well, kind of centered at the right value. Let's go ahead and do it. Yep, this one here is. And if we increase it even further to 10,000, we should see even better agreement on average with the ground truth. Here there's maybe the number is too big. Let's go back to 1,000. So it's pretty close again to my ground truth. So that summarizes the demonstrations for Chapter 1. The next computational video will cover the demonstrations for Chapter 2, but I would recommend going through the lectures of Chapter 2 before looking at the demonstrations. And with that, thank you.